Hello everyone and welcome to the next webinar series. This is Aparna Deshmukh. I'm Technical Director with Next and I will be your moderator for today's session. So we are excited to dive into our today's webinar titled Can Ground Penetrating Radar, that is GPR, help detect glass fiber reinforced polymer GFRP bars? A PDF of this presentation can be found in the handout box. You can use the PDF to follow the presentation and take notes if you desire. You may also use question box to ask questions during the webinar, and our speaker will address them at the end of the presentation. For continuing education credit, attendance for the entire duration of today's live webinar will earn you a certificate of completion for 1 PDH. Your certificate will be available in ACI University under the Certificates tab within 2 days. For those who cannot join us live, the on-demand recording will be made available about a week after the live presentation. ACI is an approved education provider for the American Institute of Architects and the International Code Council, and this webinar has been approved for one learning unit. Please take note of our disclaimer on the screen for the next webinar series. Now let's begin with a brief description of our today's webinar. This webinar will explore the effectiveness of GPR in detecting non-metallic reinforcement like GFRP, focusing on key factors such as rebar shape, size, and GPR antenna frequency. It will further discuss a comparative study on two commercially available GPR devices for scanning a concrete slab that is reinforced using ribbed GFRP bars. Our learning objectives for this webinar are as shown on the screen. Let's welcome and introduce our today's speaker. Dr. Hamid Lacy is the co-founder and structural engineer at F'(C) Solutions Incorporation, specializing in advanced non-destructive testing and evaluation of concrete materials and structures. With over 15 years of experience in the concrete industry as an engineer and researcher, he has extensive expertise in non-destructive testing, digital inspection, and special repair solutions. Dr. Lacy holds a PhD from McGill University and is a licensed professional engineer in Ontario and British Columbia. He is also the member of ACI Committee 228 on non-destructive testing of concrete. So Hamid, welcome to the next webinar series and let's listen to his presentation.
Good afternoon, everyone. And thank you, Aparna and Next, for providing this opportunity to present on this topic for your audience. So for the purpose of today's webinar, this is going to be a relatively short and straightforward presentation with the aim of answering or addressing it's a better term to use, some of the questions and concerns on the application of ground penetrating radar for detecting non-metallic rebar in concrete. So in this presentation, we will review what GPR is. Like, this is going to be a very brief introduction to GPR. So I'm not, my aim here is not to make you an expert in GPR. So it's going to be a brief introduction to main topics and what is important and what is not. Then during that, I'm going to review how GPR devices usually help engineers and technicians detect subsurface targets, let's say rebar, void, or anything else. And then the key topic of this presentation is going to be on the applications and limitations of ground penetrating radar for detecting non-metallic targets, subsurface targets, of course. And then for this, I'm going to present you a case study that we have done. This is not a research project, so this is not an academic project, so the scope is going to be very narrow, but it's a very good review and very interesting results, and I hope this opens window for many other researchers and engineers using this and sharing their experiences and thoughts. So what is GPR? GPR, ground penetrating radar, uses electromagnetic waves, electromagnetic radio waves to detect subsurface targets. So a commercially available GPR unit in the market has typically two antennas. One is the sending antenna and one is the receiving antenna. So it sends electromagnetic waves, and the decay and reflections of electromagnetic waves are received by the other antenna, and they are processed and converted into what we see as GPR signals. So the image on the left is typical, like a handheld like GPR scanner for concrete. Now, like in next few slides, you will see like we have tons of different like GPR units. They each have like different applications and perhaps different like limitations. But the core concept of like this sending electromagnetic wave remains consistent. So once we are like trying to scan an area using a GPR, whether it is concrete or soil, there are a couple of parameters that is important. Since GPR uses electromagnetic radio waves, a couple of parameters that are always important to consider when we are like looking into the test results is what frequency are we using to generate the signal. So as we know, lower frequencies tend to penetrate deeper. So most of the applications in geophysical surveys tend to use lower frequency GPR antennas. Now, once you use lower frequency antennas, you get the penetration depth that you need, but it comes at a cost, and that is a lower resolution for shallower targets. So the items that are like the targets that are closer to the ground level are going to be harder to detect with those like low frequency GPR antennas. On the other side of the spectrum, we have high frequency antennas. High frequency antennas tend to scan like a limited depth. So let's say for concrete, a typically commercially available GPR unit can scan up to 500, 700 millimeter. That's about like 20, 25 inches. And in this limited range, they generally produce a very good resolution. And that is why a higher frequency antenna is generally #1 tool for many technicians and engineers in the field to locate steel reinforcement, conduits, and things like that. Now, the second parameter that is important in a GPR signal when we are processing the data is the amplitude of the signal. So the signal that is coming back from when it is reflecting or refracting from the interface of like two mediums, let's say interface of a steel rebar and concrete. The amplitude is important when you are doing your analysis. So any change in amplitude can be one of the interesting parameters for studying. And since electromagnetic waves travel through different mediums, one of the key parameters that is important for like doing a good job is having a good understanding of like the dielectric properties of the material. Now, again, I'm not trying to be very technical on the physical concepts behind this, so very general. Just to give you an idea, GPR radio waves can travel around 0.3 meter per nanoseconds in air. So that is a pretty high speed. That's a very high speed impact. But when we switch to other mediums, so we don't want to find rebar in air. We want to find rebar in concrete, of course, or we want to identify GFRP bars in concrete. Now the landscape changes. Now when we go to concrete, the relative dielectric permittivity from 1, which is for air, increases to approximately 7 for concrete, typical concrete. Like I would say, depending on the moisture content, we are expecting any value from 4 to 10. So let's for now stick with 7. The key like objective here to show you the differences. So as you can see, these are the materials that we are using. Now, what I want you to look into here is like air versus concrete versus the steel. So there are order of magnitude differences from air to concrete, like 7 times. Very different type of responses when you move from concrete, which is 7, to steel, which is like infinite. But then numbers that we can find for like GFRP glass fibers in the literature, they are in the range of like 5, 6. Now, 5, 6, and 7. We find ourselves in a very like delicate situation, in a situation that like these two dielectric properties are very close to each other and make the like reflection, which I'll show in the next few slides, a little bit tricky to distinguish. Now, the core concept here, like when detecting metal and non-metal or any other target, is how much energy gets reflected at the interface of medium 1 and medium 2. So let's say here we do have like a concrete and a steel, okay? And then concrete is going to be medium 1 with dielectric permittivity of E1, epsilon 1, and then for steel, epsilon 2. Now, the GPR reflection coefficient can be calculated based on the values that you saw in the previous table. So let's do a quick comparison between concrete steel and concrete GFRP. As you can see, when we are like scanning through concrete to detect steel reinforcement, the amount of reflections, the energy that gets reflected at the interface of concrete and steel is almost 100%. It means like the good thing about this, it makes steel a very easy target to identify within concrete. So you reflect, all the energy comes back. What is bad about this is that like if you have too many reinforcement or a congested rebar at the top, you are basically very much limited to that depth. Moving beyond that is going to be super tricky. So if you have like a wire mesh system, for example, that is why most people who are scanning for wire mesh find it difficult to go with a single antenna and finding like any target underneath the wire mesh. Now with GFRP, as you can see, the difference between dielectric properties is not that significant. Therefore, the reflection coefficient is also going to be much smaller. As you can see in this quick example, we see that the energy that is reflected at the interface of concrete and GFRP is approximately 8%. That is less than 10%. So we are really different in the order of magnitude, 10 times the lower like reflection values. So this is a limitation that we have to live with it, and that is why what makes this topic interesting for me and for many other researchers. So this is the presentation that I'm doing here. I'm not saying that I'm the first one who is doing it. So in fact, in the literature, if you search this paper is an attempt on using multi NDT technologies like ultrasonic pulse echo and GPR for detecting embedded FRP reinforcement. Now, this was a very good research when I was like looking into it, and then the major outcome for this was that GPR can potentially identify GFRP bars. So this is a quick and simple and basic answer to the question of this presentation. So can we detect? Yes, we can, but terms and conditions apply. So this presentation is about exploring some of those terms and conditions. Of course, this is just the beginning, and I hope many other researchers come forward to bring all their like fancy analysis solutions on GPR and try to make this happen, which is going to be a very big help for non-metallic bar manufacturers because that is one of the key questions in the industry, in construction industry. One of the problems they bring to the table is that we cannot detect these bars, so repair and maintenance might be problematic if we want to alter. Who is going to find those rebar and avoid cutting bars? So this is a good attempt, and let's see what do we have to present. So with that, I start the second part of this presentation, which is a very small case study on using GPR for detecting GFRP bars. So in this like limited research, I am not looking in all non-metallic bars. I am just focusing myself to glass fiber reinforced polymer bars, GFRP bars, and this is a concrete sample that we had the chance to test at MSD bar facilities in Ontario, Canada. Thanks to them for allowing us to experiment with these with their concrete sample, which was a very unique opportunity. This is, as you can see, I would say one-to-one scale like type of construction. So the item where you see the heat map, this serves as the balcony, serves as the concrete slab interior, and the one after the thermal insulation, that is the balcony, and you can see the guardrails and everything like for your like visual clarification. So this concrete sample was approximately 10 feet long. It was 3.5 feet like wide, and the thickness was about 8 inches, so 200 millimeter. And the reinforcement, it had GFRP reinforcement, MSD rebar, of course, and the concrete was 40 MPa concrete. And the bars that was used for construction of this slab, the main flexural and transverse bars were number 15 bars, so 15 millimeter diameter you can expect for them. And the cover thickness was approximately 1.5 inch, which is about 45 to 50 millimeter. And now that is like by design, but then we haven't measured actually what the real cover ended up to be. But let's start with those numbers and see how far we can go when we are using our GPR. So these are like the concrete samples in the making. Again, photo credits goes to MSD bar. Thanks for providing this to us. As you can see, like concrete is reinforced in both directions, and we go to the next. Now, for the sake of this limited scale research, we use two different like concrete scanners, two different type of like concrete GPR scanners. The one on the left is a 1000 megahertz concrete scanner. So this is only used for like a rebar scan. We have had so many successful like projects with this unit for when we were doing conventional steel reinforced concrete slabs. So great device when we are doing like concrete scans for general applications. On the right hand, we have a device which works slightly different. So instead of like having a unique central frequency of 1000 megahertz, this one is called a step frequency antenna. This can somehow sweep from 400 megahertz to 6000 megahertz. So you can see that we are basically going from low frequencies to very high frequencies, which is very interesting because that is one of the aspects that I would like to emphasize in this presentation, that one of the limitations of detecting GFRP bars in concrete can be addressed by using a handheld probe that has a right frequency range. Okay, so, and it is not just limited to the devices that I am showing. These are all like rental devices, so there is no recommendation. It's just like trying to put the emphasis on the frequency here. So just to give you an idea, like we did several like line scans, and we did a few area scans on two sides of the slab. Generally, they are identical, so I'm not going to showcase all of the test results here for you. It was for our own sake to see if we can somehow repeat the experiment, which was the answer was okay and yes. And we wanted to see some of those like minor changes from area 1 to area 2 and some of the line scans. And now that you know like where approximately the location of the scans are, and what was the detail of the scans, you can go back and kind of like remodel and see how things are expected to be when we do the GPR scan. Now let's go and see the fun part, which is the actual GPR results. Now the GPR results, the first glance is like very different. Very different. Like you can see that like key targets are kind of repeating in the two scans, but the scan that is using a higher frequency antenna is bringing an absolutely crisp resolution. So you can find all the head of the hyperbolas which match the location of like reinforcement. So just to give you an idea, this is transverse bar. So this is when we start scanning along the long direction of the concrete slab. And then, as you can see, like this bump when we are passing over the thermal break, you can see this hyperbola that is associated with the thermal break. So that is a subsurface target that is kind of repeating itself in both antennas. So we can see that in the 1000 megahertz antenna. We can see that in the step frequency antenna as well. But let's say we are like concrete cutting technician, and we are asked to drill a hole next to this like thermal break. When we go and see at the 1000 megahertz like result, and we see like it is very I'm not trying to say it is impossible. It might be possible, but it is very difficult to find with enough confidence a location to put your like core drilling machine and take a core. Whereas when you are like scanning with a higher frequency module, the clarity is superb. Another important aspect is the second layer of rebar. Again, with the higher frequency antenna, you can see that the second layer of this reinforcement, the lower mat, is very easier to detect using a higher frequency antenna than when we are using a lower frequency of 1000 megahertz antenna. This is what we expect. Like this is quite normal. So I'm not trying to say like we have discovered something like phenomenal. No, this is what we actually expected, like from the literature as well. But another like basically proof that a higher frequency can provide a much better resolution when you are doing your job. Now, as you remember, like those, the concrete slab was sitting on a steel frame, and you can see the traces of that steel frame in both scans here. So this is the steel support on the left-hand side, and you can also somehow distinguish the back end reflection from the back end of the concrete slab, which is calibrated for the depth of the concrete, because here we had the luxury of getting the thickness measurement like very right. We had access to both sides of the concrete element. So here we had that luxury, and it helped us like do a little bit better when we are like locating the rebar, especially in terms of like depth, because finding the distribution of bars is question number one, where they are located, how deep they are located. That is question number two, which in general, even when you are doing steel, needs to be validated. Now, for that purpose, I have it in other slides. I'll get to that. But before that, let's go to transverse scan. Let's say when we are scanning along the width. Okay, so now the rebar spacing in this direction is generally smaller, and when we look at the scan that is collected by 1000 megahertz antenna, we see that the resolution of the scan is generally poor. In this one, I would say like I tried my best to try to identify targets, but I never have like enough confidence in calling them rebar. So 1000 megahertz antenna kind of like is very limited when it comes to identifying GFRP bars. So that is observation number one. Now let's go to step frequency. As you can see, the top mesh is super clear. We can easily identify all those top GFRP bars, which is great. And if we look harder, like we can find traces of like lower math as well. So here. There is also one hyperbola here that is missing. I forgot to put the pink dot, but again, not 100% confidence level, and that is normal. So we are trying to push the boundary here. We are like going at approximately 12 14 inches deep, which is deep even for steel reinforcement to identify like with like enough clarity, but it was a good try, and I was quite happy about this. Again, you can see the back end reflection here at the bottom, and you can see traces of like metal pieces connected to concrete at the support level. Very good reflections captured by the higher frequency antenna compared to the ones with lower frequency antenna. So this is really distinct difference between the two levels, two range of frequencies. Now, if you are like using GPR in your day-to-day practice for like steel scanning, you may have faced the hyperbola dilemma. Like a hyperbola formulates are used to basically calibrate the dielectric constant that you use for your concrete. So if you know, like a concrete that is dry has a different dielectric properties from a concrete that is wet. So the concrete dielectric properties can easily be altered with the moisture content of concrete. So if you are scanning a concrete after a rainy day, it's going to show you different depths. So again, in terms of like horizontal scan, horizontal distances between the targets, no problem about that. Okay, so both of them are going to deliver you the adequate accuracy. But when you are like looking in the vertical axis, which is like the depth, if we don't calibrate, we will always be wrong with our assessment. Now, calibration can be done in two ways. Like the more accurate way that I always prefer, even with the steel reinforcement, is when we do coring and going up to the level of reinforcement, actually measuring that and using that as a way to calibrate our dielectric properties to just get that particular reference rebar at the depth that is measured physically. So that is approach number one. But then hyperbola formula, hyperbola matching is a mathematical simulation technique that helps you get an estimate, a very good estimate of like dielectric properties of like the medium that you are testing. Now, if you remember, like in the table that I showed you in the early stage of this presentation, we were like talking about a GFRP having a dielectric constant of lower than 5. Now, if we calibrate these results here, with the thickness of the slab, uh, because we know the thickness of the slab is sharp 8 inches, like 200 millimeter, and we calibrate our GPR scan back-end reflection to get that 200 millimeter slab, and then go to the hyperbola to see what hyperbolas are matching with this graph. Then dielectric constant that I calculate for this concrete is going to be sorry, here I mentioned it for GFRP. For concrete I have to correct this. So this is dielectric concrete. This is 7.9 or approximately 8. Again, if you remember in the table I referred to as concrete having 7, 4 to 10. 7 is a good estimate, and again here you can see 7 and 7.9, which is not the way too off. Okay, so it's a good way. So we are not way too off, and we can identify those. So one of the research topics that is interesting for me, and I want to know like if other like GPR practitioners can provide feedback later on, is that like does like the hyperbolas from like GFRP differ from hyperbolas from like steel bars? And I don't think so, but that's one of the topics that I personally want. I'm very eager to learn more about it. Now with this, we went to the second stage of like GPR scanning. We wanted to give area scan or grid scan a try and see if we can get something like with adequate resolution as well. Now, again on the left, with that is the grid scan performed by a 1000 megahertz antenna. So basically this grid is a superposition of like all the line scans that was collected. So when line scan don't have the desired resolution, it's very obvious that the area scan shouldn't have desired resolution as well. So, and that is obvious in image on the left. But when we go to the step frequency antenna, we had a kind of a very decent like line scan, but the area scan module like algorithm doesn't like replicate the same level of like resolution that was the case for like the line scans. Now one might argue that like the start end point of the lines was not as adequate as accurate as possible. That might be an acceptable like argument in many cases, but here where we try to have a very systematic grid, so I still don't know like why we don't have a very good resolution when it comes to our like area scans. I expected like something better. I can still get like some of the key like parameters like the spacing between bars in two directions, but it's I had the expectation that this can be enhanced. Now with this quick research, what I learned personally from this experiment was that like rebar sizes that we use, like number 15 bars, 15 M bars, were generally easy to detect using GPR with higher frequency. Lower frequency GPR was less sensitive, I would say, to this bar. So one of the topics that we can try for expanding this the scope of this research is like, is it going to be the same if we go with larger bar diameters? And in a similar way, another valid question would be what would be the performance of a step frequency unit if we switch from a 15M to 10M, and then that is one of the interesting questions that needs to be answered, because many projects, many concrete slabs might have like number 10s time to time, and then if that is the case, we want to make sure like our GPR, a higher frequency GPR, is still capable of like detecting those bars. Now, one of the discussions that we had with peers at previous ACI was like the rebar shape. So one thing that was interesting and is very good regarding MSD bars is like they are pretty much similar to steel reinforcement, but we know like there are other non-metallic bars in the market that are like either smooth or grooved or like sand coated. Are those type of interfaces going to have the same type of response using like when we are scanning them with GPR? When we go back to the like literature, the research in University of Florida, we can see like that GPR were capable of like detecting smooth bars as well, like smooth GFRP bars. But I think like personally, I believe that further research is required to get a very firm conclusion on this. Now, what level of like dielectric differences, like constant differences, are there? Like how the geometry of the interface layer is going to enhance or like enhance the resolution or decrease the accuracy? That is another topic. So for future like researchers and tech practitioners can take these two into their research. Now, for myself, like, and the main key takeaways for this presentation and quick study was that GPR can potentially identify GFRP bars. Okay, so that is item number one. So the statement that we had in the older time that you cannot detect any non-metallic or any GFRP bar using using GPR. Now we know that there is a room for possibility. So that there is a chance that we can be successful with GPR. Also, by literature and our study, we have like an understanding that detecting larger diameter bars is generally easier. So if you have a number 20 is easier going to be detected compared to when we have a bar number 10. The other element is like when we have like near surface rebars, they are generally easier to identify using the GPR scanner. We saw that in the in the GPR scans for both like high frequency and lower frequency GPR scanners, the top mat was always like easier to detect. So that is going to be the case, and that's also very true about like when you are doing a conventional steel reinforced concrete slab. Another like important takeaway here is that a higher frequency GPR antenna is clearly has the advantage of in detecting non-metallic GFRP bars compared to lower frequency antennas. So if you really want to give this a try, make sure that you take the right tool to your job site. So that is the last item that I wanted to emphasize in today's presentation. And with that, like I stop my presentation here and open the floor for your questions. Thank you very much for your attention.
Thank you so much, Hamid, for such a wonderful presentation. It was very comprehensive and easy to understand. Let's go with some question answers. Our first question is, if there were both GFRP and steel bars in the same element, do you think it may be possible to tell them apart using GPR?
This is a very interesting question, and if you remember, like at the beginning of the presentation, I was talking about like a couple of parameters that is important, and one of them was amplitude. I never used amplitude in this presentation, but amplitude might be an interesting parameter to study when we are studying the different types of materials. Again, like I expect, because the reflection coefficient is going to be significantly different when we are like reflecting from steel to concrete to steel interface compared to like concrete to GFRP. I think there is going to be a different type of response at the head. So I believe this can be detectable.
Great. That would be very helpful. So our next question is, do you think rebar spacing can affect the resolution of the scans?
I believe yes. I believe yes. That is very true for steel reinforcement. So I think like when we are scanning like GFRP bars, that is going to be a valid question again. Let me go back to one of these scans, because this is one thing. One of these scans, if I remember, like. Okay, I don't have it here like in my slide deck, but in one of the scans that we did, we passed across a number like 15 bar and a number 10 bar, lapped together, like and that was a very interesting observation, because I could detect like a second like hyperbola, although with a much lower intensity, and I think. Uh, it really depends on the sizing and the spacing. So I think like if they really get too close to each other, there's a chance that we miss finding them. And if we give them like adequate spacing, so here we saw that like a spacing of like 6 inches is definitely very easy to detect, and anywhere from 0 to 6, like I think it's going to be a very interesting topic.
Oh, great. Our next question is, so it is about, I'm just going to read it out. Maybe you would get the reference. What about some amount, like 2%, 5%, or so on, by weight of nano metal particles in the resin? So maybe the participant is asking if
Okay.
there is
Yeah.
some metal particles in the resin, is it possible to use GPR? That's
It's a very good question. Like I was like driving today, and I was like having this question in my I was fantasizing about this. What if like one of those like strands in the GFRP bars had like metallic properties, just to make it like more distinguishable. I am not a GPR manufacturer, so I'm not the best person to answer that. Maybe if somebody comes up with those type of like bars in the future, we are very interested to give it a try for sure.
okay. Thank you. Our next question is, how does the change in concrete moisture affect the detection of GFRP bars?
I have not studied this aspect. This is something that we can easily do, but I haven't done it yet. But it's a very good and valid question.
Okay, great. Our next question is, does the ratio of fine to coarse aggregates affect the GPR scans?
I think it does. And this was a like relatively fine aggregate concrete. So I think maybe one of the reasons for the level of clarity that we had here in this presentation was that we were using fine aggregates in the concrete. So again, this is not a PhD research, so I don't have answer to all of those questions. But definitely, if somebody wants to like come up with a big answer to the question of like can GPR detect like non-metallic GFRP bars. They will need to study the influence of like aggregate, the ratio of aggregate. So, but again, a very valid question.
Great. Thank you so much. Thank you, Ahmed, for answering all the questions and sharing your experience with non-detective NDT for non-metallic. I think it's a fairly new emerging technology, and I hope it grows further. So, with this, we end our question answer session. So before we go, I have few announcement. I hope you all can see the screen. Yeah. So this is the list of the upcoming webinars at ACI University. Please visit aciuniversity.com to register for the upcoming webinars. So, and this is another note that NEXT is organizing 2 full-day webinars, one on structural rehabilitation and strengthening using FRP composites in mid-September. We have most of the speakers, so I think it's that day is good to go. But if there is someone who is still interested, please send the abstract and we will check if we can accommodate. Our another one is on advancement in polymer utilization in 3D printing construction industry, which will be in mid-October. The timeline is still there, 1st August. So if any of these topics are of your interest, please submit an abstract, which is up to 300 words, including the duration of your presentation at info@nonmetallic.org. With this, once again, thank you all. Thank you for the participant. Thank you, Amit, for the presentation, and thank you for being with us. And with this, we end our webinar. See you all at the next webinar. Bye-bye.
Thank you. Thanks for the opportunity.